So we're also very happy and privileged to have our next speaker, Professor of Astronomy and the Director of Undergraduate Studies at Harvard, Karin Öberg. She focuses on chemistry. We've heard a lot about physics and astronomy at many conferences in biology, and we're going to focus now more following up the chemistry that Jonathan talked about with her research. She is an astronomer, and she studies how chemistry affects star and planet formation, and as a very interesting byproduct of that process, the likelihood of forming habitable planets, the ones we're most interested in, of course. Recent highlights of her research include the observation of snow lines. For those of you who are interested in going skiing on your next trip, you can ask her where the best locations are, and organic molecules in solar nebular analogs, where exoplanets are in the process of being formed. She received a Hubble postdoc fellowship and joined the Harvard faculty in 2013, I think, right? At Harvard, her research in astrochemistry has been recognized with the Sloan Fellowship, a Packard Fellowship, and the Newton Lacey Pierce Award. And she's also one of the directors of the Society of Catholic Scientists. And she's going to talk now about the likelihood of extraterrestrial life. Please join me in welcoming Karin.
So what I want to talk about is, speculate wildly about, is the likelihood of extraterrestrial life. So this is only going to be slightly south of the first talk in terms of speculation, and only one or two actual sort of scientific results to support some of those speculations. But the first thing that I want to just, make a distinction is what kind of extraterrestrial life we're talking about. And I want to split them up into three. So this morning, of course, earlier this morning, we heard about the how we should think about extraterrestrial rational life, and that would be one category that I would also like to split out. But the other two would be what we might think about as single-cell bacterial. I hesitate to say simple life because I did that once, and then some biologists got really upset with me calling a bacteria simple, but simpler than when we think about animal life. So those are the three categories that I would like to think about separately as having different perhaps different likelihoods of existing. So starting with the sort of bacterial, simple, single-cell kind of life. So here we're really talking about the likelihood of life originating at all on other planets. And when astronomers think about the likelihood of life outside of Earth, when Jonathan already talked about thinking about it within the solar system, they think about planets in the so-called habitable zone that Jonathan already mentioned. So these are planets that are sitting at the right distance away from their star, where they're not too cold and not too hot. And they're not too cold and not too hot for liquid water to exist. The reason that we think liquid water is so important for a possible origins of life is that liquid water, oh wow, this is awesome. My distinctions. We are already here. Actually, we moved on to the habitable planets. So when we're thinking about these potentially habitable planets, we're thinking about them as being places where liquid water can exist. So the first question we would want to ask then is, if you have a planet that is at the right temperature for liquid water, does it actually have liquid water, or is it just a dry planet at the right temperature? As I was starting to say, the reason we're so interested in liquid water in the first place is that this is just a fantastic medium for molecules to come together to have chemical reaction in it. So the second question we would like to ask then is, if you have a planet that has liquid water, does it also have these kind of molecules in it that could get reactions going towards an origins of life? Or is it just a wet planet, but a pretty boring and dead one? Ultimately, the way to answer these questions is to actually get data on these exoplanets. And the easiest way to get data, as Jonathan indicated, is to look at signs in their atmosphere or what's going on their surface through spectroscopy. Even with the James Webb telescope, fingers crossed, knock on wood, intercessions to St. Albert the Great and the other protector of natural sciences, even after James Webb flies, this is going to be extremely difficult for Earth-like planets. And this is really going to be a process over the next many decades to get this kind of data. But that doesn't mean that we don't have any idea of how likely it is to actually find the right ingredients for life on these planets. We can think about the likelihood of that from what we know about how planets form. So planets form as byproducts of stars, and stars themselves form by the collapse of parcels of the medium between stars, the so-called interstellar medium or interstellar clouds. As this collapse continues, you release gravitational heat. This release of gravitational heat heats up the center. That's where the star forms. But then these clouds always have a bit of rotation or angular momentum that needs to be preserved, and that leads to the formation of one of these disks that you see in front of you. And in these disks is then where planets form. So how often do planets form in disks that are rich in water and the kind of organics we think are important for origins of life chemistry? Well, water is the easy one. So the reason that this image is all in blue and has these sort of watery trails connecting the different phases of star and planet formation is that it's meant to illustrate that water is extremely abundant in space. Just as it's very common in the solar system, it is very common where we look where planets and other planetary systems are coming together. The question about organics is a bit more difficult to address, but one of the things that we have started to do, and this was alluded to in the introduction, is looking at these planet-forming disks and looking for organic molecules in them. Currently, we primarily do this using ALMA, which is a wonderful telescope done in Chile that allows us to do rotational spectroscopy on these disks as a means towards detecting molecules in them. We will also be able to use James Webb to do something similar, but with vibrational spectroscopy. And I have just put basically all the organic molecules that we have found in disks to date are the ones that you're seeing sort of pasted on top of this disk. In particular, and this is the one science image that I'm going to show, one of the molecules that we're finding is hydrogen cyanide. Hydrogen cyanide is an interesting molecule, and I'll come to a moment why I'm focusing on it. But here I'm mainly first using it as an example of what we can do with a telescope like ALMA. So these are chemical images of hydrogen cyanide in 5 of these planet-forming disks, where we have we have evidence of that planets are assembling right now. So what you're seeing is that we have basically isolated the microwaves or photons that are coming from hydrogen cyanide, and that allows us to see not just that hydrogen cyanide is there, but also how it's distributed in these disks. And we see that it's abundant, and we see that it's distributed across most of these planet-forming disks. And that's actually true for basically all these organic molecules that we can see in these disks. Now, the reason that I focused on hydrogen cyanide is that there is at least one plausible scenario that took us here on Earth from a simple chemistry into the formation of all the building blocks of biomolecules as they exist here on Earth that has hydrogen cyanide at its center. Jonathan already alluded to this, that one of the possibles or chemical precursors of life, and I find it to be a very plausible one, involves being at the surface of a planet where you have access to UV light. You probably want to sit in a pond rather than in an ocean, which is sort of shown here. And you have hydrogen cyanide and some sort of sulfuric or sulfides kind of compounds as well. So if you do have that, it's actually pretty easy to go, as I said, to the basic building blocks. So things like amino acids, the building blocks of RNA and DNA, building blocks of cell walls, and so on. This means that we have at least one pathway that takes us, from simple chemistry towards biology. So this is a sketch then of how would you consider then going further. Well, after you have these building blocks of the building blocks of life, the next step, and this is indeed a very challenging one, is to figure out how these building blocks start to assemble in ways that produces something that's something similar to what RNA is today. Something that can carry information, that can copy itself, and that can partake in metabolism one way or another. This is not a solved problem, but it is a scientific problem that chemists right now are trying to solve. How you could basically go from the prebiotic chemistry step here up to the last universal common ancestor, which is the kind of cells that we are all made of. In addition to that, I think there are more and more sort of pieces of the puzzle that are being laid, which is, to me, very comforting. There's also another way we can look at it that, to me, suggests that life originates pretty readily if you have something like Earth's condition. And that's if we look at the timeline of how life originated and developed here on Earth. So what this shows, and the main thing I want to focus on now, is just how soon after the Earth became anything close to habitable, so as soon after it's starting to cool down, that we have the evidence of the first life here on Earth. It just seemed to happen very quickly if we compare it to the lifetime of a planet. But this is speculation. We don't yet know how life originated here on Earth, and therefore we don't know if it is indeed, yes, it happens quickly if you have the perfect conditions kind of thing, or if it's something that generally happens as long as you have the most basic conditions available, basically water, organics, maybe UV light as well. Before going on to sort of the next steps, which is, well, if you get the first step on this timeline, you always get to the animals and maybe even to rational animals. I do want to do a very brief theological checkpoint. How should we think about this in relation to creation as understood in the Bible, in the sort of Christian theology? So there are two sort of potential issues that I've heard raised, none of which I think are very serious, against the possibility of life elsewhere. One is, you would perhaps call it the dinosaur problem. Extraterrestrial life is not mentioned in the Bible, neither are of course, famously dinosaurs, and therefore one might be tempted to think that it doesn't exist. This is, I think, in this audience, not a very convincing argument, hopefully. And I just wanted to mention it, that this would fall in that same kind of category, and therefore, to my mind, not be a very serious one, as we have plentiful evidence of life forms existing that are not mentioned anywhere in the creation story. I think the more interesting one is that one way that one can imagine that God gives evidence of his governance of the world is by having some transitions being miraculous. And one that has been proposed to fall in that category is the origin of life, this transition from chemistry to biology. And if that is indeed how you perceive that God's governance is primarily revealed, is through these miraculous kind of transitions, then the discovery that life is abundant across the universe, which really would support that it is a natural process happening through secondary causes, might threaten that kind of perception. This is definitely something that exists in some Christian circles. It is not the traditional Catholic way of thinking about how God's governance is revealed in the universe. That's rather the opposite. That is like through the order, through the laws that we observe. And if if it indeed is what I think it will be revealed, that we do see this evolution from chemistry to biology happening in a very regular way, that would actually just add to the law of abundance and to the order that we have in the universe. It would also, I think, lead to some very interesting thinking about the philosophy of chemistry and sort of the potential directedness of chemistry towards biology, given the right conditions. But that, I guess, is more philosophical than theological question. So if there are no, as I can see, as far as I can tell, any theological objections to sort of abundant extraterrestrial life, does that mean that it doesn't have any theological relevance at all? I don't think so. I think the kind of universe that is revealed to us, if it is one where life is overabundant versus one where we are the only life, the only living planet in it, they're quite different. And to me, they suggest this sort of, it's called different personality of the Creator. And I do hope that it is the overabundant creativity of God that's going to be revealed through further explorations. But I can't deny that also the opposite, that this is it, that this is the living planet, has a beauty to it as well. That would make us the ark, carrying all life forms with it through time and space. So I spent most of the time talking about just the origins, the possibility of any kind of life forms outside of Earth. I do briefly want to spend a little bit of time on the other two categories, so the possibilities of animal extraterrestrial life as well as rational ones. The only thing I want to say really about the possibility or the plausibility, the likelihood of extraterrestrial animals is that it's not obvious to me that just because you find some, let's say, bacterial extraterrestrials, that you will always see an evolution into extraterrestrial animals. One of the ways to look at that is just to return to the timeline of life here on Earth. So we just saw just a few minutes ago that it didn't take long after the Earth became habitable for it to become inhabited. But it did take a long time to then have animals. This suggests that there might be a second bottleneck that, as far as I know, is not yet fully understood. Why we spend so long being basically single-cell bacterial, and then you get this Cambrian explosion, and we get all kinds of life forms. But it was a long time in between, and that to me suggests that we can't assume that this will always happen. This seems like something that requires some specific things to develop on a planet, which may or may not happen. But if we do get to animals, should we expect to always get to rational animals, to ensouled rational animals like ourselves? Here too, I don't think this is something that can be taken for granted. Even if we think that we will always develop intelligent animals once we have some sort of animal form. If we look again to Earth, we are far from the only biologically human species that have wandered the Earth. These are some of the other human species that have been discovered, some of which our forefathers interbred with, so definitely something we would call human. As far as we can tell, though, only one of these humans, and only after quite some time, became ensouled, became a rational animal. And one of the sort of scientific evidence of that, so not even theological revelation, comes to just looking at what kind of artifacts they have left behind. And in particular, the kind of the kind of artifacts that include art is something with some interesting caveats that we only see with Homo sapiens and only start seeing after they have already existed as a species for a long time. This means that we cannot, I think, automatically assume that just because an animal develops sort of the biological capacity to be fitting to be ensouled with a rational soul, that they become rational animals. This, of course, fits rather well with our own understanding of our own origins, which is, it has two parts to it. One is the molding out of the clay of the earth, while the other is the very specific breathing in of the spirit of our souls into us. This means also that if we do find extraterrestrial rational species, they have very specifically been created by God, and that should be, I think, somewhat reassuring to us. Now, if we should find them, if they should exist, this presents theological puzzles. That was, what we heard a lot about this morning, how we should think about their salvation, their connection to God through their own incarnation. This is just an excuse for me to show Giotto, really, but it depends really on which day you're talking to me, like what I think could possibly be the answer there when it comes to how to think about incarnation versus extraterrestrial rational animals. On the one hand, I find what Chris was talking about this morning extremely appealing. There's something that feels just about it, that we all, in some sense, got an analogous interaction, analogous story, and an analogous friendship with God, if indeed these extraterrestrials do exist. But there's also not just my gut reaction against anything that seems to threaten the honor of Our Lady, but there's also, when you think about the incarnation of God, the creator of the cosmos, stepping into the cosmos himself, that to me has somewhat more of the feel of the Big Bang to it than the formation of a star or a planet. Now, whether that gut feeling is right or not is, of course, highly up for grabs. And I said, I do find it very appealing to think that other extraterrestrial races would have had the same kind of friendship and experience with God as we did. But if they don't, and if my gut feeling is right, that leaves us again two not very appealing choices. One would be that, they don't exist, and I really don't hope that is true. And the other would be that somehow they are saved through the incarnation of the second person of the Trinity as Jesus Christ of Nazareth. And that certainly has a lot of theological puzzles with it as well. So if I am to end, it will be to end with that I really hope that Chris is right. And with that, thank you for your attention.
Well, thank you, Karin, for those beautiful reflections, and we're so glad we're able to see these images as well. If I can ask you the first question, I'll sneak in here. When you ask an astronomer what they mean by a long time, it's always a dangerous question because there's so many scales, but one thing that caught my attention is the time between first ensoulment and art. You reflected that took a long time. What did you mean by that?
So actually, what I meant to say is that almost the opposite. So that biologically, Homo sapiens existed for a long time before we see any evidence of them being ensouled with a rational soul. Now, whether they started creating art immediately after they were gifted with a rational soul, I think is something we can only speculate about. I like to think that they started very quickly to do it. That just seems like such a human, theologically human thing to do. So, yeah, sorry about that.
It's going to be fun to find out when we find out. Okay, thank you. Other questions? Steve has one in the back.
Hi. I wonder if we could focus on the left-hand side of your timeline, the early bacterial, or whatever that's called, the early life, and compare that to the ongoing lab experimental programs to create life in a bottle, and whether those are anywhere close to saying anything interesting about, about whether this is some kind of potentially repeatable process where we know with these exact mixtures it happens, and with this energy source it happens. But I don't know what the status of those research programs is.
Yeah, no, thank you for that question. And here I am going to in part reveal my ignorance as a once chemist and nowadays an astronomer, but I'm going to try to at least give some hint of what's going on. So there are multiple issues, so like multiple puzzles that needs to be solved between this sort of prebiotic chemistry step and the others. One is simply how you start building large enough molecules in high enough concentrations that you can even hope to start building some functionality. There have been some steps forward in that there seems to be a little bit easier than people maybe thought 5-10 years ago. So Jack Szostak at Harvard does a lot of work on that, and I think there has been real advances. Doesn't mean it's a solved problem, but it seems to be moving in the right direction. That they basically, how do you start connecting these building blocks when you don't have enzymes around to help with it? And it seems to be a little bit easier than maybe they feared it would be. So that's one thing people are working on. The other is once you do have these kind of sort of like small, something like RNA chains or maybe even something simpler but still can carry information, how do they actually maintain their information? How do they replicate? And how do they, in some sense, take part in converting energy like metabolism? There are also, there's some things there that seems to be a little bit easier again than chemists thought just 5 or 10 years ago. But again, we're very far from, it's like these giant puzzles. And I think actually some few pieces have been put in there in the past 5 to 10 years, but as a whole, it is still very far, I would say, from actually having life in a bottle. But you will hear there are some of my collaborators who are more optimistic than I am.
Okay, I think we have time for a couple more questions.
Thank you. That was a very, very interesting talk. Where I'm usually struggling with is exactly that step that we're just discussing, from the prebiotic chemistry to something that can store information and has functionality. And from a statistics point of view, we have an N of 1. So how can we possibly assign any likelihood to that? So it could be a singular event, or it could be very common, but we have really, from a mathematics point of view, no way of telling, right? And your argument that it happened relatively early, maybe in 200 million years, that for an N of 1, that doesn't fully convince me, because if it had happened like 50 times in a certain period of time and we could do a probability distribution on it, then I would probably buy it, no pun intended. But with an N of 1, it makes it very difficult. So the actual question I wanted to ask is, it seems to me that there is some sort of a negative connotation to the idea that this could be a singular event. Why do you think that is? Why are we afraid, in a way, of contemplating that this could be a singular event in the universe?
Yeah, so first of all, I mean, of course, what you said first, as sort of the context, is correct. I very carefully avoided assigning any numbers, and I think that is correct, or even to say what I meant with likelihood. So I'm not sure that I would want to classify it as fear or anxiety over it, but I think if you, as a scientist, want to try to figure out how this happened, it in some sense can't have been a singular event, because then we're never going to figure out. So I think at least sort of operationally, we're going to have to treat it like something that has actually fairly high probability of developing in this way. And that may or may not be true. I think the way that we ultimately will be testing it is, first of all, with the missions within the solar system. I mean, I think that's the short term. A negative there would not tell us a lot, but the positive would, of course, tell us tons, right? And the same thing with the exoplanets, especially in the early days, when I think at most we will get to a few exoplanets where we can rule out sort of Earth-like life, which even that is not very satisfying. But again, a positive would tell us a lot. And in the meantime, I think it is the right thing operationally to do, is to think that there is something in the chemistry that is sort of directed towards developing biology, and try to see if you can find it. While keeping, I think, staying humble and keeping very cognizant, and like keeping in mind that this might be totally wrong, and this might be, the 1 in a billion kind of thing, or maybe even a singular event. So I think I mostly agree with you.
So I don't see Steve with his microphone. So, oh, there you go.
So I don't know if there's going to be a question here, so I apologize, but I want to follow up on the N of 1 in statistics in the horribly physicist way and probably annoy every chemist and biologist in the room, so apologies ahead of time. One of the things I find fascinating about thinking about the probabilities of these, I feel like I come to a conclusion the probability is 1 for the following really bad reason perhaps, but maybe really good. You know, I study, this is fundamentally a nonlinear, non-equilibrium system, and so I think the interesting question is the mechanism, and my analogy is convection in fluids. So when you heat a fluid from below, it forms convection rolls with a probability of 1 at the right temperature difference. But if you look at it statistically, how to get all those molecules to move in that organized fashion, the probability is 0. Right? The probability becomes 1 because of the non-equilibrium dynamics and the nonlinear dynamics, and it's a very different way. Now, thermal convection in fluid, way simpler than this, I admit. But it's still, the physicist in me says, we don't know the details yet, but that's okay. I kind of know the broad thing. There's a non-equilibrium, nonlinear system in a particular range of parameters. This is what always happens. And I think the interesting question is, what are the elements that go into those parameters? And is the occurrence of the parameter singular, not the process? So I put a kind of different lens on it to get to my probability of 1 for life elsewhere in the universe. I just had to put, I was trying to come up with a question and I couldn't. So my question is, did that make any sense to you?
Nice save. So I guess my only comment on that sort of question is that it is in my mind mainly sort of rephrasing the same sort of uncertainty, which is well, I guess taking out miraculous event, which I think we have already done, which is this a process that requires such specific and therefore so unlikely conditions to all come together at any one planet that it basically only happened on Earth. I think in some sense, but if you do have those conditions, it's the likelihood of 1. At least from an astronomer's point of view, I'm not sure that that makes such a big difference compared to just thinking about it as a general process that always happens when you have the most basic ingredients there, versus a close to singular event that we can't hope to either find on another planet having happened or recreate in a bottle. So I don't think I disagree, but I'm not sure that there was actually any disagreement.
So let me ask our president what time lunch is.
Lunch is 10 minutes ago, so I think we should probably...
So let's thank our speaker.